Welcome. Thanks for coming to my lecture on GPGPUs, General Purpose Computation on Graphics Processors. I have 1 hour to talk about topics on which people have taught entire courses, programming in Cuda and OpenCL. I'll devote most of the time to talking about Cuda. It's a general purpose programming environment that Nvidia has developed for programming on its hardware. OpenCL is an industry standard that is currently in 1.0. The platform is not very widespread or very well adopted yet, but it might be in the future, so it's certainly worth spending some time on. My name is Mark Murphy. I'm a fourth-year grad student here at Berkeley. I spend most of my time writing parallel code in Cuda and OpenMP. The other names there, Brian Catanzaro gave this lecture last year. So most of the slides started off as his. All of the content on OpenCL I stole unaltered from Tim Mattson. So first, the agenda, I'm going to spend a minute or two on shameless self-promotion. Then I'm going to give you an introduction, an overview of GPGPUs, the evolution of graphics hardware, and a quick toy example. I'm going to tell you about the hierarchy of parallelism that Cuda lets you express, the memory hierarchy in which you have to fit all of your data, how these things map onto actual Nvidia hardware, and then I'll go through as much of the OpenCL information as I have time for. I have well over an hour of OpenCL content, but I won't get through nearly all of it. So first, advertising. For anyone who is at Berkeley and wants to take an entire course on parallel computing, Kurt Koitzer and I are teaching CS 194.15, titled Engineering Parallel Software. It's targeted towards undergraduates, but I imagine that first-year grad students might get some benefit out of it as well. The goal is to teach everything you need to write efficient, correct parallel software for many-core processors. That means Intel multi-core, Intel, who's funding the course, and I managed to get some Cuda in there as well. So there will be plenty of practical experience writing parallel code in the context of a small video game I've been writing in my spare time over the summer. Screenshot there. So on to the introduction to GPGPUs. So GPU hardware over the past 10 years or so has evolved from highly specialized, non-programmable, fixed function units for doing essentially the basic tasks of graphics. That is, taking a three-dimensional scene and rendering it onto the 2D screen of your monitor, plus things like texturing for deciding what colors pixels are. But as the demands of graphics became more intense computationally as well as more flexible, more general purpose, GPU hardware had to become programmable and had to become more powerful at a rate far faster than CPUs have. Essentially, up until the introduction of Cuda, it was programmable, but very, very difficult to use. And Cuda and now OpenCL are making that much, much easier to do. So basically, CPU architectures over the past 20 years or so have been using Moore's law increase to increase cache, make the pipelines more complex to improve the performance of legacy workloads, while GPU architectures have been trying to provide as much DRAM bandwidth and on-chip parallelism as possible, and to become more and more general purpose, but targeted mostly at highly data parallel workloads. So the Cuda programming model is intended to make GPU hardware more accessible. So there's sort of two sub-goals here. One is to be inherently scalable. So data parallel programming naturally fits well onto a wide range of architectures. So you have on the far left here, on the upper graph, GPUs like the 8300 GS and 9400M that are typically in the chipsets of laptops. So they have very small number of cores, so 8 and 16 floating point pipelines. On the far right end, you have the GTX 480, which is the latest, biggest, and most powerful, which has 480 floating point pipelines. Cuda wants to be a programming model that lets you write the same program and get as much performance as you can out of all of these different processors. So the way that GPUs pack so much hardware into a finite amount of space is SIMD, so single instruction, multiple data. essentially the goal is to make SIMD hardware accessible to general purpose programmers. Otherwise, you waste most of the hardware that's on your chip. So if you have 16-way SIMD, which is essentially the width of the latest Nvidia processors and also the ill-fated Larrabee chip from Intel, 94% of the computation is tied up in this SIMD hardware. So this goal of scalability, I'll elaborate a little bit more. So in Cuda, you express many independent blocks of computation. In a minute, I'll tell you exactly how you do that. But the essential source of the scalability is that you tell Cuda that these blocks can compute in any order. So you say, I have 10,000 blocks to compute. You decide which order to compute them in. So the multi-threaded Cuda program can run either 2 at a time on a GPU with 2 cores or 4 at a time on a GPU with 4 cores. It'll take half as much time on the GPU with 4 cores, but it doesn't matter that you're computing them in different orders. And so this is how many programs achieve linear speed up between GPUs of the same generation, essentially. So SIMD programming. Hardware architects love SIMD because it's a very efficient way to put more hardware, more computation on a chip. You basically copy and paste your floating point pipelines, and then you can amortize the energy and performance cost of fetching and decoding instructions. The problem is that standard SIMD instructions on CPUs, SSE, et cetera, are pretty inflexible and difficult to use, so much so that a compiler can't really target them. They have very difficult restrictions in terms of memory access patterns, the kind of things you can and can't compute. Cuda will provide a threading abstraction where essentially you'll consider each SIMD lane a different processor, an entirely different processor that's completely independent of the others. And then the hardware will recognize the important special cases where they are actually executing the same instructions. So first things first, I'll tell you the nitty-gritty, some amount of it, of how to actually write Cuda programs. So it's standard C, C++ syntax with a minimal set of extensions to give you access to the hardware that the GPU actually has. So I mentioned this multiple instruction, multiple data thread abstraction that will execute in SIMD on the actual GPU. So you write a thread, you say execute this thread this many times, and then the hardware will do that for you. There's a certain hierarchy of these threads that will give you access to certain features, let certain sets of these threads communicate and synchronize, and then a library of intrinsic functions for giving you access to special purpose useful hardware on the GPU. So to define a function which will run on the GPU that you will call from the CPU, you add this global tag. To define a function that will be callable only from the GPU and that will execute on the GPU is this device tag. You can use a similar set of tags for variables. This shared tag essentially means a variable that only exists on chip. I'll talk in much more depth about shared memory in a minute. When you want to go and call one of these kernel functions from the CPU, you have this triple angle bracket syntax to specify how many times to run that function. Again, I'll explain that what a block and a thread is exactly in a minute. And we have these dim3 types for specifying the size of blocks and knowing who you are essentially when you're inside of a thread. And then various intrinsic functions for for math.h functionality, for example. From the host, there's a similar set of library functions. So to allocate memory on the GPU, you have malloc and free, just like in standard C. And then there's memcopy functions to actually get data to and from the GPU. So Cuda is inherently heterogeneous. You write code that runs sequentially in a thread on the CPU, and that sort of orchestrates the execution of massively parallel code running on the GPU. These Cuda memcopies are the basic way that you communicate between the host and the device. This goes over the PCI Express link in your system, which is very slow. It's relatively high latency and low bandwidth. So you want to sort of minimize, for the sake of performance, the amount of data and the number of times you do those transfers. So time for hello world. In parallel computing, hello world means something trivial done on vectors. So what we will, here is a C program that implements vector addition. We just take every element of two vectors A and B, and we add them up and write them into the corresponding element of C. In standard C++ code, we have this vec_add function. We give it 3 pointers and a length of those arrays, and it's just a for loop. On the host, we have to allocate and fill some arrays and then call our function. To change this into a parallel Cuda program, we have to just essentially add a set of tags. So the first thing we've done is added this global tag at the very top to specify that this should be compiled to run on the GPU. Rather than iterating over an index I, each thread will use this block index, block dim, and thread index to figure out which element of the array it's supposed to work on. And then the for loop also turns into this if I less than n check, because we may have more threads than we have elements in the vector. And then the exact same code that was inside the for loop is now just the body of this kernel function. On the host, instead of using new or malloc, we use this Cuda malloc function, which specifies that the variable A should hold a pointer to data on the GPU. And then we have this triple angle bracket syntax to specify that we want vec_add to run n times. Here I've added 255. I've rounded n up to a multiple of 256, and then specified that there should be 256 threads in each block. So getting simple Cuda programs working is very easy. It's a very moderate change from sequential C or C++ code, although for performance you then have to do a lot more, and we'll talk about that later. So briefly, the Cuda software environment is very mature. The NVCC compiler works from the command line, much like any other C++ compiler, ICC or GCC. You give it C++ source code, it gives you a binary to execute. There's a driver that you have to install in your machine to manage the low-level interaction between the host and the GPU. But that's portable. That driver exists for Linux, Windows, and Mac OS. The Cuda SDK has many code samples demonstrating all the things that Cuda can do for you. You don't have to install that if you don't want to, but it's nice when you're learning. And library support is continuously growing. There's versions of BLAS and FFT, and a proprietary version of the LAPACK libraries that's in development. And there's a lot of industrial adoption going on. If you go to the Cuda webpage, they'll tell you many things. There's the Nvidia Developers Conference in a few weeks where you can go and see even more. So moving on, I'll tell you now about the hierarchy of threads you can specify, so essentially explaining that triple angle bracket syntax. So the Cuda programming model is, to some degree, independent of the actual GPU implementation of it. There actually exist in research, mostly at UIUC, compilers that will take Cuda code and run it on multi-core CPUs. That's the mCuda project of John Stratton. There's a project to compile Cuda to run on FPGAs. So there's a lot of this that is just good practice for organizing data parallel code. The only production quality implementation of Cuda is Nvidia's compiler. And so I will talk about the GPU architecture simultaneously with describing the programming model, but they don't have to be conflated this way. So a crude analogy, which does pretty well, is to consider the GPU a collection of these streaming multiprocessors, which are essentially the same size as a single core of a multi-core CPU. So this cartoon at the bottom here is of the GTX 480, the latest Fermi architecture. It has 16 of these streaming multiprocessors. The streaming multiprocessor has a large number of SIMD execution pipelines that you should consider much the same way as SSE execution pipelines, at least for the sake of understanding performance. Each SM has a single set of control logic, a single register file, and a single L1 cache, much the same as a CPU core. So the Cuda thread hierarchy is essentially 4 levels. This highest level of streams is actually optional. If you don't specify any streams, Cuda will provide a default stream for you. But a stream is a list of these grids that will execute in order. You can have a large number of these streams, and the GPU will execute from all these streams in parallel. There's currently a limit of 16 streams, but that will change in the future and get larger. Each grid is a set of up to 32 thread blocks, and all of these thread blocks will be executing the same kernel function. A thread block is a set of up to 1,000 Cuda threads, which execute one instantiation of your kernel function. Before Fermi, this limit was 512, if you have older hardware. Each Cuda thread is an independent, lightweight, scalar execution context. So and there's this extra detail that becomes important, actually, that groups of 32 of these threads form warps, which execute in lockstep. And that's how SIMD is handled by the hardware. So going into more detail, these CUDA threads, logically, each one is its own independent multiple instruction, multiple data execution context. It has its own program state in the same way that a P thread or a Win32 thread would have its own control flow, program counter, copy of the register file, function call stack, etc. It can load from any address in the GPU DRAM, much the same way that a thread on a CPU could. So if you saw the talks about MPI, there's this notion of a rank, where you can sort of identify yourself as a thread. In CUDA, there are actually 5 integers you use to identify yourself, your thread index and your block index. The thread index is potentially 3-dimensional. Frequently, you just use only the first dimension. Same with the block index. The thread index identifies a particular thread within a thread block, and the block index specifies the thread block you're in. So although it is an independent execution context, it's much finer granularity than a CPU thread, in that you need many, many more of these to actually get any work done. So at full occupancy, that is, when you have as many threads as the GPU can actually hold, each thread has 21 32-bit registers, and that's the entirety of its state, essentially, at least if you don't want to take a big performance hit. 1,500 of these threads have to share a 64 kilobyte L1 cache. You can choose to execute fewer threads than that, and again, we'll talk about the performance optimization details a little later. But each of these threads has a very small share of that cache. Moreover, each thread won't execute very fast at all because the GPU doesn't have any operand bypassing networks, and it only very recently had added caches. So functional unit latencies, memory access latencies, all have to be hidden either by multi-threading or ILP within a thread. The easiest path is actually to hide it by multi-threading. So a CUDA warp is the logical SIMD execution width of the CUDA processor. When you're in the early stages of implementing a CUDA program, you actually don't need to worry too much about warps. It's almost entirely a performance optimization detail, but it actually turns out to be one that's pretty important. So these 32 threads execute simultaneously. That is, within a given cycle, they will, at least a logical cycle, they will all execute the same instruction, have the same view of memory. The execution hardware is most efficiently utilized when all threads in a warp are executing the same instruction. That way, you can fetch the instruction once, decode it once, and then execute it 32 times. If they diverge, that is, start executing different instructions in the same cycle, some execution pipelines will go unused. They use essentially the same mechanism as vector predication, if anyone's familiar with that terminology. And with respect to memory access, if all the threads in a warp are loading or storing an aligned contiguous block of DRAM, those 32 accesses will be dynamically merged into a single high bandwidth access. That actually turns out to be the most crucial thing for improving the performance of a CUDA program. And there isn't a particular identifier for it, but you can identify your warp by dividing your thread index by 32. And technically, this number 32 could change in future architectures, but it's baked into a lot of programs, and a lot of optimizations you can do require that you know the warp size. And so it's unlikely that they'll change it, although they've technically reserved the right to. So a Cuda thread block, a good way to think about it is a virtualized multi-threaded core. We'll talk more in detail later, but it essentially is equivalent to one of those streaming multiprocessors. You dynamically configure the number of Cuda threads, the number of registers, and the amount of L1 cache it has access to at kernel call time. So you don't have to know at compile time how big one of these things is. You can specify it when you know how big your actual data set is. So it includes some number between 1 and 1,024 Cuda threads, and they all have the same block index identifier. So you need to map into one of these thread blocks a data parallel task of moderate granularity. So the working set should fit into the 128 kilobyte register file and the 64 kilobyte L1 cache. So the register file, notice, is twice as large as the L1 cache. And in fact, the L1 cache is, the aggregate L1 cache is much larger than the L2 cache that exists. So this inverted memory hierarchy is intended to support largely data parallel workloads where all of the work is happening at the leaves, basically. So the non-cacheable working set is limited only by the GPU's DRAM capacity, which is on the order of, for small GPUs in laptop chipsets, a couple hundred megabytes. For the largest Tesla chips, 6 gigabytes. And all threads in a block share this instruction cache, but otherwise can execute absolutely independently if they so please. But again, as I mentioned with the warps, it's most efficient when they are sharing the same small program. The most important feature of a thread block is that the threads within that block can synchronize via barrier-like intrinsics. I'll talk about them more in detail in a few slides. And they can communicate via fast on-chip shared memory. So this L1 cache can actually be configured as a software-managed memory. So instead of a hardware-managed cache, you can specify exactly what what data you want to be there, and you can do arbitrary shared memory communication very quickly within a thread block. A Cuda grid is a set of thread blocks that were all called from the same line of code from the C++ running on the host. All thread blocks and all threads within those blocks have the same entry point. The thread blocks within a grid differ only in this block index number initially, although there's no reason at all for different thread blocks to try to do the same thing if it's convenient for them not to. Like you can switch on your block index and you incur no additional penalty because the thread blocks likely have different instruction caches, for example. You want to have many thread blocks per grid to try to, it's a good idea to try to have a grid occupy the entire GPU. 1 to 8 thread blocks execute on each of those streaming multiprocessors, depending on their resource usage, essentially. And I'll talk about that again later. So the thread blocks have to be parallel subtasks of one larger computation, that is the grid. The program must be valid for any interleaving of the block execution. So you can't really assume either that all of your thread blocks will be resident simultaneously on the GPU. And if you have fewer cores than thread blocks, then they certainly won't be. And even though the memory system is flexible enough for them to communicate in arbitrary ways, the memory system and the various intrinsics that I'll discuss in some detail later allow you to implement producer-consumer relationships or spin locks or semaphores, although that's very risky to do precisely because you don't know that all of those thread blocks are resident simultaneously. But things like shared queue indices are okay, where they can coordinate on some piece of memory as long as you don't assume any ordering between thread blocks or assume that all thread blocks will be resident simultaneously. So the highest level of the thread hierarchy is the stream, which, as I mentioned, is optional. If you recall that vector add program I showed you before didn't have a stream specified, and so Cuda would have just put it all in the default stream 0. But if you want multiple kernel calls to execute simultaneously, or you want to overlap transfers over PCI Express with kernel executions, you need to use streams. So the concurrent execution of multiple kernel functions will actually only happen on Fermi hardware, the GPUs released just this year. But on pre-Fermi devices, you can overlap transfers over PCI Express with kernel execution. And so this snippet of code down here creates some of these stream objects, does an asynchronous memory copy on 2 different streams. Those memory copies may happen simultaneously. And these 2 vector add calls, where I can be adding 2 different vectors. If neither of these 2 vector adds is large enough to saturate the entire GPU, Cuda might execute them both on different halves of the GPU. So now I'll start talking about the memory system, which it will turn out is the most important thing to consider when you want your program to actually execute efficiently. So the Cuda memory hierarchy starts with the per-thread local memory, and which is essentially a backing store for the register file. Each Cuda thread has private access to a configurable number of registers. This number of registers is actually specified at compile time. The compiler does register allocation of the variables in the program and then decides this used 23 registers. There's actually a compiler flag that you can use to limit the number of registers it will use. So if the default register allocation would produce 23 and you only want to use 16, you can force it to do so. Although it then may need to use the local memory. There's actually nothing local about the local memory in the sense that it lives off chip in global DRAM, and it's used as spill space for registers and the call stack. On Fermi, it's cached though, so it's not too big of a performance hit. That is, there's at least 16 kilobytes of L1 cache shared by many threads, and there's the 768 kilobyte L2 cache as well. Each thread block has private access to a dynamically configurable amount of scratchpad memory. So this is that on-chip SRAM that you can use either as 16 kilobytes of L1 cache and 48 kilobytes of software-managed scratchpad, or you can configure it vice versa, 48 kilobytes of L1, 16 kilobytes of scratchpad. There's this Cuda func set cache config thing that you use to do that. Look in the documentation if you want to use it. But this is the amount of scratchpad memory is specified dynamically when you call the kernel. It's actually an extra optional argument to that triple angle bracket syntax. Before Fermi, there was only 16 kilobytes of SRAM per streaming multiprocessor, and it was 16 kilobytes, and you could only use it as scratchpad. But if you specify using less than 48 kilobytes of scratchpad, then you can map actually multiple thread blocks per streaming multiprocessor. So if you don't use any, then the only limit to the number of thread blocks that can be resident on a streaming multiprocessor is the number of registers that each thread block uses. So essentially, since all these things are configurable, you have a trade-off between the amount of concurrency that each SM is executing and the amount of state that's associated with your program. So the next level is the global memory. So on Fermi, the global memory is cached by an L2. This L2 cache is shared among all the streaming multiprocessors, so it's trivially coherent, whereas the L1 caches are incoherent. You can't, if you write data into the cache of one streaming multiprocessor, it will not be seen by the other streaming multiprocessors until it's written back out to DRAM. And I'll talk about ways to control that behavior in a few slides. But all thread blocks in a grid access the same pool of DRAM. So this global memory has to hold the persistent state, whereas the registers and the L1 and the scratchpad all hold temporary state of the program, essentially to the local working sets of your subtasks. This global memory is much more expensive than the on-chip memories. You have at least 100 times the latency in terms of number of cycles. The registers are 0 cycle access. The L1 cache or scratchpad on Fermi is on the order of 10 cycle access. it might be 20 cycles to get to the L2, but it's several hundred cycles to go off chip and read something from DRAM and bring it back. The aggregate bandwidth of the on-chip memories is also about 100 times, 50 times or so. I forget what the exact number is, but much higher bandwidth in aggregate to the L1 caches versus this global DRAM. Although the bandwidth of this DRAM is large. You have, on a moderate-sized GPU, about 100 gigabytes per second access to this DRAM, whereas on a typical CPU, you may only have 10 gigabytes per second. So kernel 0, if it executes sequentially with respect to kernel 1, can write information out to DRAM. When kernel 0 exits, kernel 1 can then pick up where that left off and use the results of kernel 0, assuming kernel 0 and kernel 1 were in the same stream. So there are a few other components of the memory hierarchy that are occasionally very useful. This 64 kilobyte constant memory is about the right size, for example, to hold convolution kernels if you're doing image processing of some kind. It's actually backed by the same DRAM that's used for global memory, but it has special 8 kilobyte read-only caches scattered throughout the chip that you can use. The Cuda texture memory is a very graphic-specific piece of hardware. Its behavior is documented in the Cuda literature, but it's only rarely useful in general purpose because its goal is essentially to take some texture, an image that you read out of a JPEG or something, and interpolate between 2 pixels. So if you want the location at pixel 3.5, it will take an average of pixel 3 and 4 for you. I've seen people find a use for that in general purpose programs, but frequently you're just as well off using the L1 cache. So their behavior is highly optimized for their graphic-specific roles, but it's worth knowing about them. One more level up, you can have multiple GPUs in your system. Each GPU has its own entirely independent global memory, and all of these global memories are separate from the CPU's memory. Again, I mentioned earlier, you allocate memory in the devices with CUDA malloc and CUDA free. There's actually a whole range of functions that let you access it in various ways. I'm not going to go into detail, I don't have time, but the CUDA documentation has plenty of information. To transfer memory back and forth, you use these CUDA memcopy functions that are very expensive. You maybe have 5 or 6 gigabytes per second of bandwidth between the CPU and the GPU, and you don't have, in the current implementation of everything, you don't have a direct memcopy from device 0 to device 1. So if you have multiple GPUs and you want to communicate data from one to the other, you actually have to transfer that back to the CPU's memory before you can transfer it to the other GPU's memory. To manage multiple devices, currently you have to use multiple CPU threads, so P threads or something, and then synchronize accordingly on the CPU. I've mentioned before, one of the most important aspects of the CUDA memory hierarchy is the communication you can do within a thread block in that fast on-chip shared memory. So in order to communicate via that shared memory, you need some way for the threads within a thread block to synchronize on that memory so that one can know when the other has produced the data it wants. So the most important one is this sync threads function, which says that no thread in the thread block will continue execution until every thread has executed that sync threads. So if you want to guarantee correctness, that is, you want to write data into your fast shared memory and then read it back out in some arbitrary permutation among threads, every thread must execute this barrier before proceeding. Sort of an implementation detail, but one that's good to know about, is that you can't have 2 sync threads on opposite sides of an if-else because the sync threads they wait for is indexed by the program counter. So different threads can't just execute the same number of sync threads. They have to actually execute the same sync threads. There are additional intrinsics that you can use to do small amounts of communication. So, for example, to count the number of threads that have a non-zero integer to do an AND across all threads or an OR across all threads, which is useful for implementing local reductions, for example. You can imagine uses for them. Here's a little code snippet that gives you where that transposes a matrix which lives in DRAM. Each thread is going to get its index into the matrix via its thread index. This shared float T will hold the matrix when you load it onto the chip, and then you can write it back out after that sync threads. The reason the sync threads is necessary is because each thread will read a different value out of this shared memory than it wrote. So if we didn't have that sync threads, then that copy from T into the original DRAM might happen before the load from a different thread. So a little more detail here. It's a crucial resource. You can express far more concurrency on the chip than you actually have memory bandwidth to support. So if you are doing all of your computations in DRAM, then the 100 gigabytes per second will usually just not be enough. And that will be your performance limitation. If you have some kind of reuse that a cache can help you with, this shared memory is absolutely crucial for decreasing the amount of memory bandwidth that you need to get from off-chip. So you can declare shared variables statically via this shared tag on int begin and end there. You can allocate entire arrays that then you can index via your thread index, for example. Or you can allocate it dynamically just by using an extern shared without specifying a size, for example, that second scratch there. And then in the kernel call, this triple angle bracket syntax has an optional third parameter, which is the size of the scratch pad that you want to allocate to each thread block. And again, most of the communication within a thread block is done via this scratch pad. You will read from, you will write some value to scratch at your thread index, and then sync threads, and then read the value that the thread to your left wrote. So it's important enough to have a third slide on it even. So there's 64 kilobytes of SRAM that's accessed fast at about a 10 cycle latency. You can divide it into 1648 scratch pad versus hardware managed cache. Again, before Fermi it was only 16 kilobytes. And unless the data will actually be shared between threads, it's usually more worthwhile to put it into registers. The register file is twice as large as this, and actually now it's faster to use a register file. Before Fermi, the shared memory was as fast to access as the register file, but on Fermi they actually had to change that. So this is a second order performance effect of bank conflicts, but it's good to mention it to you so that you're at least aware of it. There's a lot more information about this and examples of when these bank conflicts can happen in the Cuda programming literature. But if you have put data in shared memory, there are 32 banks that are addressable independently, so that all 32 threads in a warp can access it in parallel without having to take any time to serialize them. If the address is interleaved, so if P is a pointer to some float in some bank, P plus 1 will point to a float in the next bank, mod 32. Each bank can satisfy a single 4-byte access every cycle. If two threads in the same warp try to access the same bank in a cycle, those two accesses have to be serialized, and that instruction takes an extra cycle to execute. Unless they're accessing the same location. So for example, if you're broadcasting one value from shared memory to all threads, that can happen in one cycle. So even with bank conflicts, though, it's usually faster to do things in shared memory versus DRAM. These atomic memory operations turn out to be very useful, although they are very expensive. So these let you access the same memory location from all threads in your program, or multiple threads in a program, either in shared memory on the on-chip SRAM or in global memory. So for example, you can sum up a lot of values quickly and dirtily by using this atomic add function, where you specify a pointer to the integer you're trying to accumulate into, and then an integer to add to it. The hardware will automatically synchronize these such accesses from many different threads and make sure that they all actually occur. If you don't use this, some of the additions may actually not take effect. If you haven't spent any time doing shared memory programming, this may not make any sense to you, but you can come and ask me later. And there are various other operations, taking the min, doing an exchange, a compare and swap, very useful for implementing, for example, spin locks, which I told you you shouldn't do. I'll say it again, they're substantially more expensive than standard loads and stores, but sometimes they're the right answer. So this issue of memory consistency, I won't go into too much detail here because people may not have much experience with this before. Again, if people are curious, come and talk to me later or send me email. But in general, you can't assume that the memory accesses that your program executes will appear globally in the same order you executed them. That is, if you store to two different locations from one thread, another thread may see those stores happen in a different order. This is just a side effect of the way that the memory system achieves its high performance. Essentially, how it gets you to 100 gigabytes per second is by making these weird things happen sometimes. So you can enforce ordering using these memory fence instructions. So all memory operations that you do before a thread fence appear to other threads to happen before all the memory operations you do after the thread fence. Frequently, you have to also use this volatile type qualifier, which forces the compiler to actually generate memory references for every pointer reference. Otherwise, it may see that you're using the same pointer multiple times and only do one load or store to that address. If that's not the behavior you want, you have to tell the compiler not to. So that was a lot of information. Now I'll try to tell you some of the same information, but in the context of the Nvidia hardware. I'll try to spend about 5 or 10 minutes on this and then go on to 10 or 15 minutes of OpenCL. So Cuda is designed to be functionally forgiving. Using only what I've told you now, you can get your programs running and correct on an Nvidia GPU, but it probably won't run as fast as you need it to. And in fact, if you don't pay any attention at all to how the program actually gets mapped onto the hardware, you would likely have been better off using OpenMP in the first place than using the 4 cores that are on your CPU. Although in some cases you can get speed up by doing homogeneous single program multiple data by launching 10,000 threads, all of which are doing this more or less the same thing, modulo control flow. But really, the hardware implementation is crucial for actually getting performance out of this thing. So I'll go through each of these in more detail. One single scalar thread essentially gets mapped to a single lane of the SIMD execution pipelines. So it may execute on a different core instruction by instruction. So for example, in that cartoon on the far right there are those special function units that are used for accelerating sines and cosines and exponentiations, et cetera, versus all these square cores that do standard floating point multiply additions, or the load store units that do memory operations. But a single thread will occupy a single one of those blocks in any given cycle. This SIMD lane will have access to some subset of the register file. The compiler and the hardware ensures that the same thread gets the same set of registers every cycle. But otherwise, that's a very small piece of the entire pie. One warp executes on a single block of these scalar cores in any cycle. You can see here that they're actually I've actually only highlighted 16 cores, even though a warp is 32. I said before, the warp is the logical SIMD width. What actually happens is that the hardware fetches the warp's instruction and then issues it on 2 consecutive cycles. This way, they can sort of pipeline the execution, and it's an efficiency trade-off, really. So a thread block, you can consider it to be equivalent to a single streaming multiprocessor. A thread block has access to as much of the register file on that SM as you want to use, as much of the scratchpad and L1 cache as you want to use. In addition, the instruction cache and the texture units, etc. One grid, that is all the thread blocks that are spawned by a single kernel call, a single line of C++ code with the triple angle brackets, can use some number of the streaming multiprocessors on your GPU. Frequently, one grid is all it takes to saturate the entire GPU, but in the case where your grids are not large enough, you need to have a set of streams to execute multiple grids in parallel to use the entire GPU. And then the aggregate state of this has to be in the global DRAM. So, quick summary there. Each level of the processor hierarchy is associated with a particular memory resource. The scalar threads and warps get some subset of the register file. A single thread block has to fit its data into the shared memory or L1 cache. And multiple streaming multiprocessors, the whole GPU, your entire grid and streams use the entire global DRAM. You need many, many threads to hide the many latencies that typically plague CPU performance. So DRAM access is usually the reason why CPU pipelines stall. How GPUs get around that is by having many threads in each thread block and multiple thread blocks on each streaming multiprocessor. The functional unit execution latency, typically 7 to 10 cycles or so for floating point operations, is hidden by having multiple warps within the same thread block executing independently. And PCI express transfers the latency of those can be hidden with streams. I've hinted at this, but essentially, since you can specify how many registers your threads use and how much shared memory each thread block uses, you can trade off the state of each thread block for the number of thread blocks that you have resident simultaneously. For example, a good counterintuitive example is the fastest matrix multiplication in the world only uses 64 threads per streaming multiprocessor, even though you can have 48 warps, which is 1,500 threads. So those 64 threads unroll their loops a lot and use a lot of instruction-level parallelism to hide these functional unit latencies. And similarly, they hide DRAM loading latencies by using the L1 cache very effectively. So, yes?
How do you know how many registers are used?
You can have the compiler print it, or you can actually tell it to just print a file that says how many. The Cuda programming documentation will tell you how to do all this, but there's compiler flags that will specify. So I have tried to talk about memory as much as I possibly can because this is a quote that I use in almost every talk I give. I think Kathy Ellick was the first one to say it. A manycore processor is a device that turns a compute-bound problem into a memory-bound problem. Essentially, the amount of on-chip computation is growing much faster than in every new generation of processor than the amount of memory bandwidth that you have. So we are at the point where you need at least about 10 times as many floating point operations for that you have memory loads. So unless you reuse every byte that you load from memory 10 or 20 times, you're going to be bound by memory. And so memory concerns dominate performance tuning. So for example, if you load a single cache line, you want to be sure to use all of it, and you want to be sure, if you can, to load single cache lines at a time. If a single coalesced load straddles a cache line boundary, then you load 2 cache lines. This is all actually true of CPUs as well as GPUs, but in GPUs the problem is even further exacerbated by the large amount of on-chip parallelism. So we have about 10 minutes left, and I'm at the end of the Cuda. So if people want to ask me questions now about Cuda at the expense of some of the OpenCL stuff, they can go ahead. Otherwise, people are more than welcome to come and talk to me after the talk. Yes?
What about the precision of the floating point implementation?
The floating point implementation is IEEE compliant. So there's single precision and double precision. The double precision is half as fast on Fermi as the single precision. And they're all to the same accuracy as they are on CPU implementations. So fully IEEE, whatever the standard number is, compliant. And in fact, for certain functions like sines, cosines, and exponentiations, there are two versions. There are fully accurate versions, and then there are less accurate versions that execute faster. And the Cuda programming manual will tell you those. So again, the Cuda programming model is just a general approach to organizing data parallel programs, but its only viable implementation is on Nvidia GPUs. So now I'll switch gears and start talking about OpenCL using slides that Tim Matson made, and he gave a very similar talk at the boot camp last year, and I stole the slides entirely from him. So first, he has this little tirade about why ugly programming models are better. So I personally think that Cuda is a very elegant programming model in that you have very small changes that you need to make to your C program in order to make it a parallel program. That is not a goal of OpenCL. So the starting point is heterogeneous computing. Modern platforms have some number of CPUs, some number of GPUs, and possibly other weird things like DSP processors or cell processors. And the goal is certainly not to offload work from the CPU to the GPU. That's not the right way to think about GPU programming, even in the context of Cuda. Really, the best way to use modern platforms is to try to use everything. Use the CPUs for the things they're best at, use the GPUs for the things they're best at. So every program should take advantage of all the computational resources it needs. And the world is getting more heterogeneous in a lot of ways, and it's very chaotic. All of these are processors that people have been excited about within the past 5 years or so. And this hasn't arisen because parallel software is easy and ubiquitous. It's because we can't make sequential processors any faster. Essentially, process technology has limited us to about 2.5 or 3 gigahertz, 3.5 if you're really lucky. But there's fundamentally this dangerous mismatch between the rarity of parallel software and the ubiquity of parallel hardware. So really, what needs to happen is there needs to be some sort of an industry standard for accessing parallel hardware if people are actually going to write maintainable parallel software. And so in the long run, Tim Matson's thinking, and our thinking in a lot of the research at Berkeley as well, is that we will provide higher level, Python or MATLAB frameworks, programming environments, and SDKs for writing parallel code, rather than having everybody program at the C or C++ or Cuda or OpenCL level. So we need some target language, basically, for these programming environments that can also be used by actual programmers who care more about their performance. So what's the solution? You just need to find a good programming model, right? Well, the number of failed programming languages is, people have been trying this for 30 or 40 years, and all of these are languages and programming environments people have come up with that eventually didn't get adopted. Tim Matson, he's been around a long time, and he's used many of them, and he hates them all. And there's really nothing new. There's message passing, there's data parallelism, there's various flavors of shared memory, there's functional languages, shared address space versus distributed memory space, and there's sort of parallel objects. But all of the things that I showed you in the previous slides are some variations on these things. So the first lesson, don't try to be beautiful. The primary difference between between the things on that entire list is the different ways in which they tried to be beautiful. OpenCL specifically tries not to be beautiful. And I'm going to skip all this in the interest of time. So software vendors, not academics trying to design new programming languages, are the ones that will eventually decide which programming model wins. So pragmatism is really the key. You need it to be portable. You need to take the same base of software and be able to run it on whatever piece of hardware you're given. So that's a strike against Cuda in that it only runs on Nvidia's hardware. And a lot of the programs I write, actually, people are nervous about adopting just because it's so tied to Cuda's hardware. Program lifetimes are measured in decades, not the 2-year or 1-year life cycle of GPU turnover. And then it needs to be predictable. If the hardware changes, if you need to change the software too much to use a new piece of hardware, it's going to be really difficult to use any of it. So we need an ugly programming model that is platform portable, and it has to be very pragmatic. So this is how ugly OpenCL is. There's hundreds of different functions. And you don't necessarily need to use all of them. They're not even readable on this slide. But various things for math and integer operations versus relational operations versus vector operations. Things that I didn't need to tell you about in order to tell you how to write Cuda programs, but things that you would need to understand in order to write OpenCL programs. So I actually think I'm going to skip this. Essentially, this is a story of the fact that, I'll just skip right to here, that OpenCL is the result of all these different companies trying to come together and agree on one programming interface for all of their hardware. So Kronos is the same organization that standardized OpenGL and continues to maintain those standards. Apple is really the driver behind all this, and all these other hardware and software vendors are involved in the process. So there is an OpenCL specification out. There are OpenCL compilers and runtimes out. You can use it, but it's so 6 months from proposal to release specification. That was a long time ago. I think that I haven't updated this slide for this year. So a high-level view of OpenCL. I have just a few minutes to get through this, and that'll be just enough. So the model of the platform is essentially the same as the Cuda model. You have some host thread managing many compute devices with many processing elements in them. So the host thread is going to do all of the orchestration of the highest level of the application, and it's going to tell these various compute units to do different parts of the computation. So the best way to explain this slide is probably just to make the analogy between things I spent a lot of time explaining in Cuda and the words on this slide. So a command queue is essentially a Cuda stream, but it has more context associated with it. That is, you associate a particular command queue with a particular compute device, whereas in Cuda you had multiple streams communicating with the same device. And again, just like you make kernel calls or memory transfer, or call the memory transfer functions, the host unqueues commands onto this command queue. The main difference in OpenCL is that there isn't a nice triple angle bracket syntax for doing so. The work items are essentially the same. You can make an analogy between thread blocks or threads and work items. And the abstract index space is essentially the same as those thread index and block index things that you had in Cuda. I guess a work group is the analogy to a thread block. So the memory model is similar. It even has some of these global constant memory things that are, there's a cache for them, just like there is for the constant memory in Cuda. And then you have private memories on each of the compute units. So I think I'm just about out of time, but I will show you the vector addition example. Again, the OpenCL code, this is the kernel function that would run on the device. Again, all it takes to change a sequential program into this is to get rid of the for loop, insert this get global ID, and then take the body of the loop and make it the body of this function, and add this kernel tag and additional tags to the pointers. The host program, however, is not as simple as the Cuda host program, essentially because they, in the quest to deal with many different kinds of hardware, they couldn't wrap as much up in language syntax. So actually underneath, the Cuda compiler generates a similar set of statements from the triple angle bracket syntax. But since they have Cuda has a much clearer picture of the hardware it's going to execute on, it doesn't need to expose any of this to you. So essentially, you define your platform, you build these command queues, you allocate your memory objects, you actually have to load the source of your program from a file and compile it, which actually Cuda does also, but again, the triple angle bracket syntax hides all that from you. You need to execute the kernel and then read the results back. So I think at this point, since I'm out of time, I will end. If people have more questions, want to know more about OpenCL, they come ask me now, or just download these slides off of the website. And yes, questions?
Giovanni Ree, I'm a graduate of UC Berkeley, electrical engineering. Where do you see the results of Cuda and OpenCL today and a year from today as far as actual released application software?
Right. So where is this all going? In 5 years, how will people program GPUs?
I'm more interested in where we are exactly today, and in a year, and if this conference happens again next year, what will be available to the consumer.
So the state today is that Cuda has been out for almost 5 years or so. I guess the first Cuda programs I wrote were in 2007 or so. So Cuda has been out at least that long. The software stack is very mature. The compilers work. They very rarely crash. The driver only very rarely crashes. And similar with OpenCL, the compilers exist, but they're not as mature. Certainly there's much more industrial adoption of Cuda because it's been around for longer and Nvidia has been marketing it very hard. I personally think that in the future, there will be the same compiler that you use for Cuda programs versus OpenCL programs, plus a preprocessor written by Nvidia to translate the triple angle bracket syntax into all this command queue junk. I mean, I think actually somebody could write that today if they wanted to. But I think that certainly the main goal of OpenCL is to provide some sort of portability. And it does that, but it doesn't provide performance portability. That is, you need to write different implementations of your code to get peak performance on different platforms. That's the main. If they don't fix that, then OpenCL will not be adopted, I don't think.
So earlier today, the four people talked on 4 different application areas.
Uh-huh.
What application software is out there today for Cuda and for OpenCL, and where do you see that will be in the next year? What application software is going to come online? It'll be available a year from today that's not available now.
So it's hard to know. So with Cuda, there's a wide range of applications. If you go to the Nvidia website, they have a whole list of success stories of people getting 100x speed up using their GPUs. Certainly people like me spend all day writing Cuda code most of the time. I have code running in a hospital down at Stanford using Cuda. There are many other stories of grad students here and people in industry doing the same thing. There are fewer of those stories for OpenCL, if any, right now, just because OpenCL is so much less mature. But the fact that all of these companies are behind OpenCL and willing to pay people to develop software in OpenCL, since it's an industry standard, they feel more confident that investment in developing OpenCL software won't be wasted. For example, in the off chance that Nvidia goes under and Cuda is no longer supported and there are no more GPUs. OpenCL would give them the confidence to actually start using GPUs in their applications. Yes?
Considering OpenCL is a rival for... It is clear that OpenCL is rival for Cuda, then why does Nvidia support for OpenCL at all? Do you think that at the back end they might not be producing optimized code or something?
Well, so I think the reason why, so I don't actually consider them to be all that much of rivals, given that there's so much analogy you can make between OpenCL and Cuda. Certainly the so almost every API in OpenCL has an analog in Cuda. It's just that the Cuda programming language gives you, nice syntax so that you don't actually have to know any of that API to use it. And there's no reason why they couldn't make the languages the same. If you thought hard enough, you could probably make the OpenCL device programming language a superset of Cuda, or maybe just have a compiler flag that says compile this as Cuda code or compile this as OpenCL code. I think the primary reason why the compilers are different is actually entirely pragmatic. A lot of the Cuda compiler uses the Open64 open source compiler infrastructure, and Nvidia didn't want to have to open source their OpenCL compiler. So they're entirely different code bases, but there's no technical reason why they should be. Yes.
So how differently would you approach, programming the CPU and a GPU? Like I'm thinking of like system of linear equations of matrix multiplies.
Mm-hmm.
There should be a different way of doing it on GPU. Right?
So certainly, if you are, if your goal is to solve a system of equations, you should just call a library that does that for you. But I mentioned there's the CU LayPack, and then there's the CPU LayPack version in ACML or MKL. But if you were going to write some piece of code and parallelize it for CPUs versus GPUs, my personal methodology for doing so is to basically target the GPU and then get rid of all the parallelization that I map to threads within a thread block. Turn a thread block into a P thread or an OpenMP thread running on a single CPU core. And then basically, if possible, map the warps into SSE instructions. But the warp is a more general object than an SSE instruction is. So that works fairly well just because the intended granularity of a CPU core, having some number of tens of kilobytes of cache and then shared access to higher levels of cache, is about the same granularity as a streaming multiprocessor. So that's really the best analogy to make. The only difference is that you have extra levels of parallelism below below the level of the streaming multiprocessor, specifically warps and threads. Yes.
How much percentage-wise do you think like a program like Jacket, which wraps MATLAB and runs it on GPUs, taps into CUDA's full potential?
It's hard to know. I actually haven't used Jacket because I just haven't ponied up the $1,500 or whatever to get a copy. But there's certainly a lot that Jacket can do. Jacket has some very cool tricks. Similar to things that have been done in research of batching up large numbers of calls to functions before trying to execute any of them. And so depending on how much optimization, you can actually get a lot there. In fact, the reason why it's hard to compile C and C++ code basically stems from the fact that it's at such a low level. Programming in MATLAB, you specify everything at a very, very high level. And sort of the parallelism is implicit there. Certainly, it's hard to have as much control over where your data lives and to control how things are parallelized. So really, to write a good Jacket compiler, they would have to make a lot of assumptions about the sizes of data structures, for example, so that they know whether it should be cached in the L1s or streamed out of DRAM. And that's really the kind of decision that I think would be more optimally made by somebody writing Cuda versus somebody writing MATLAB. Okay, if there are no more questions, we're past time by about 10 minutes.
And let me just thank everybody for attending, all of those present and many of those absent on the web listening. Thank you very much. We have a great deal of fun preparing this every year. We also try to change it every year based on your feedback. So please expect to get an email request to fill out a little form to say what you like, what you didn't like, what we should do differently. One piece of feedback that we got already is please have a panel where all the speakers get together and where we can have a more kind of informal discussion with everybody, you know, agreeing or disagreeing with one another up on stage. So if you can think of anything else, that's fine. You'll get email from us. Some other folks, I think, asked to see the Parlab. Not that it's that exciting, a physical space, but you're welcome to walk over and with us and look at that too. So thank you very much, and have a good rest of the semester.